Welcome everyone. This is Danny Anyag. This particular chapter, which is chapter 3, is a continuation of the simple memory systems that we discussed about a couple of weeks ago. And today we're going to focus more on the complex systems using virtual memory management. So the learning objectives for this one is as follows. As you can see in this chapter, we will follow the evolution of memory management with 4 new memory allocation schemes. This memory allocation schemes, these are the schemes that remove the restrictions of storing the programs contiguously, all right? And most of them eliminate the requirement that the entire program reside in the memory during execution. These are the 2 most important criteria that really fell short with the simple systems we discussed a couple of weeks ago. So we're going to also, as a conclusion to this chapter, the importance of using cache memory and how the use of it actually improves the performance of our CPU. So let's try to look back on what we have covered so far with regards to the 4 memory management techniques. So if you would recall, there were 4 memory management techniques we presented. These are, number 1, the single user systems, the fixed partitions. The third one, I believe, is still dynamic partition, and the fourth one being the relocatable dynamic partitions. Although they have differences, they all share the requirement that the entire program, number 1, must be loaded into memory, and 2, they should be stored contiguously, and 3, that they remain in memory until the entire job is completed, meaning there is no preemption whatsoever. Consequently, each puts severe restriction on the size of executable jobs because each one can only be as large as the biggest partition in memory. These schemes laid the groundwork for more complex memory management techniques that allowed users to interact more directly and more often with the system. In the next slide, I'm going to basically show you the complex systems that piggyback from the simple systems using virtual memory and how those disadvantages I've mentioned, 3 distinct disadvantages. Number 1, they all has to be loaded into memory, the entire job, that is. They have to remain in memory until all the jobs have completed. And number 3, they have to be stored contiguously. How these restrictions can be worked around in order to have a multi-processing kind of environment. Yeah, the simple allocation schemes, we can see that there are still some problems. Each one is required the memory manager to store the entire program in the main memory at contiguous locations. We need to find a way to avoid having to keep the whole program into memory to run and the restriction of storing the programs contiguously. What if we could divide the jobs into 2 separate smaller chunks? Actually, we can with virtual memory. It is a solution. And we will look at the evolution of such memory allocations, actually 4 of them. Let's start with the page memory allocation, allowing us to divide the job into 2 equal-sized parts. The sections of a disk are known as sectors or blocks, and the sections of main memory are known as page frames. Before executing a program, the memory manager makes some preparations. First, it determines how many pages are in the program, and then it locates enough empty page frames in the main memory so that it can pass all the pages into them. The adjacent memory blocks do not have to be loaded in as adjacent memory blocks. They can be stored in any available page frame in the main memory. Now, this is a more efficient scheme, but it does come with a little complications. We need a way to keep track of all the page locations, which increase complexity in the operation. Through the use of 3 tables stored in the part of the main memory, we can keep an eye on locations of various jobs. First is a job table, which is a dynamic list that contains 2 values, the size of the job and the page map table location of that job. The page map table then contains important information for each of the pages, the page number, and its corresponding page frame. address. Finally, the memory map table has one entry for each page frame, listing both its location and status, in informing whether it is busy or in a free state. Now that we have an understanding of a page map allocation, we can now see how demand paging works. It's very similar to the previous concept, but the main difference is that the pages are loaded in on demand, meaning that the pages are only brought into memory when they are actually needed. The page map table we looked at before increased with 3 more columns. One to determine if the page is already in memory, known as the status. The second to check if the page has been modified. And a third to check if the page has been referenced recently. How do we determine the replacement of pages? By using a page replacement policy. First in, first out, least recently used, least frequently used, and most recently used. These are the policies used to change pages based on a specific algorithm. These are all pretty self-explanatory, and I'll simulate this later on in later slides. So I've looked at page map allocation and demand paging, but what else is there? Well, we've looked at separating the jobs into 2 pages. But what if we could break it down even further? We can actually, it's called segmented memory allocation. This splits the job into 2 separate segments that reflect the nature and structure of the code. Usually, when you view a script, it is separated into individual functions or subroutines that can be called one at a time. You may have a function called add that makes a calculation of the 2 numbers, and a function called divide, for instance. We can call this one after the other, and they will run in the chosen order. Now, take all of these functions and label them as segments. Instead of using a page map table, we now have a segment map table that makes a list of all of the various size segments that need to be put in the main memory. That is the process. Now, we move on to the final scheme. It is a mixture of segmented and demand paging memory allocations. It offers the logical benefits of the segmentation idea, as well as the physical benefits of paging. There is no new logic involved, but there are some minor modifications to consider. It makes use both of the segment map table and the page map table, plus additional information of authority to read, write, and execute a file. A major disadvantage of this is the overheads and the complexity that goes with it, adding more tables to handle the load. So why do we use virtual memory? It's a good thing, actually. Let's say we currently have a RAM that is fully occupied and has no time for jobs waiting to be slotted into it. Because we use segmentation and paging, we can exceed the amount of memory space that we need and put everything on the hard drive. Although it's a slower alternative, it can act as an extension to the RAM. So now that we have a brief overview of each of those 4 complex memory management systems, let's now go down to the detail or the granularity of those memory allocation. So just to reiterate, page memory allocation is based on the concept of dividing jobs into units of equal size, and each unit is called a page. Some operating systems choose a page size that is the exact same size as a section of a main memory, which is called a page frame. Likewise, the sections of a magnetic disk are called sectors or blocks. Remember this, that the page memory allocation scheme works quite efficiently only when the pages, sectors, and page frames are all the same size. But definitely if they're not, it'll be much slower. Let us now talk about the advantages and disadvantages of page memory allocation. Specifically, one of the huge advantages of a paging scheme is that it allows jobs to be allocated in non-contiguous memory locations, allowing memory to be used more efficiently. However, there are disadvantages such as overhead is increased and internal fragmentation is still a problem. Although it occurs only in the last page of each job, nevertheless, it is profoundly significant. The key to the success of this scheme is the size of the page. Like I said before, a page size that is too small will generate a very long page management tables, while a page size that is too large will result in excessive internal fragmentation. Determining the best page size is an important policy decision. There are no hard and fast rules, and definitely it is a hit and miss sometimes. Demand paging introduced the concept of loading only a part of the program into memory for processing. It was first widely used scheme that removed the restriction of having the entire job in memory from the beginning to the end of its processing. With demand paging, jobs are still divided into equally sized pages. When the job begins to run, its pages are brought into memory only as they are needed, and if they are never needed, they're never loaded. Demand paging takes advantage of the fact that programs are written sequentially, so that while on one section or module is processed, other modules may be idle. Not all the pages, however, are accessed at the same time, or even sequentially. As we just learned, the policy that selects the page to be removed, the page replacement policy, is crucial to the efficiency of the system, and the algorithm to do that must be carefully selected. There are several such algorithms that exist, and it is a subject that enjoys a great deal of theoretical mention and research. The book basically presents two well-known policies, the first in, first out, and the least recently used policy. In this demo, I am going to show you how these two algorithms are actually simulated, and we'll introduce, as an added extension, two other very famous algorithms, which are the least frequently used and the optimal replacement policy. So here, straight the first in, first out replacement algorithm. The rationale behind this algorithm is that the assumption is that the page that is in the memory the longest would have the least chance of being called upon. So it is the best page to remove. That is why it's called first in, first out. So this particular algorithm has been used in the earlier operating systems, OS2 warps, and even the very old PC-DOS based operating system. So here's how this actually works. Let me show you a simulation. Here in this diagram, I have here basically 9 data pages, or basically 10 data pages that I need to load into the memory. And the assumption is that we have 4 frames, okay, in the memory. You've got frame 1, frame 2, frame 3, and frame 4. All right, so what we're going to do is we're going to simulate the contents of the page frame in the RAM as the job comes in. So since there are 10 data pages or 10 jobs, we're going to look at how the page frame's content changes over time. And in so doing, we're also going to take note of how many page faults or page interrupts there happen. Page fault is, the definition of this is that whenever a data page is required by the memory manager and it's not in the page frame currently, then that's a page fault, or otherwise known as page interrupt, which our reference textbook would like to call it. It's a page hit if the data page that is being called upon is already existing in the page frame. And at the end here, we're going to actually try to get a statistics of how much or how many page faults were there and how many page hits were there in terms of percentage. So let's get started. So the first one is the data page that is being required is page 1. All right, in the frame you would see there's no data page that is loaded, so right off the bat that's a page fault. All right, so we'll put there an F, and then we're gonna load 1 right there. The second job that needs to be called upon is data page 2. As you can see, data page 2 is nowhere found in the current page frame, so that would result into a fault, and we're just gonna put their 2 together with 1 that's already existing in the memory. Data page 3 is called upon. As you can see, 3 is not yet in the page frame, so that will be a page fault. So we're going to copy 1, 2, and then 3 gets loaded. Same thing with the next job, which is data page 4. 4 is not there, so that would result in a page fault. And we're going to copy 1, 2, 3, and then data page 4 will be loaded into the RAM. The next page that needs to be that is being called is page 1. As you can see, page 1 is already in the page frame right there. So that would result into a page hit. So here we're just going to copy 1, 2, 3, and 4. We don't need to pull the data page 1 from the hard disk because it's already stored in the RAM currently. So the next page that is called upon is 2. As you can see, 2 is also there. That would result in a page hit. All right, so 1, 2, 3, 4, it will remain to be the same. The next data page that will be called is 5. As you can see, 5 is not currently in the RAM, so that would result into a page fault. We're going to put there an F, and then we're going to find out, okay, based on the algorithm's nomenclature, first in, first out. So we're going to look from left to right, and that's the reason why I have this yellow arrow line pointing from left to right. So we look from left to right from the contents of the current page frame. So you got 1, 2, 3, 4. You got that 1, 2, 3, 4. So the first page or the first data page that got in is actually 1. All right, so 1 would be the candidate to be replaced by 5. So here I'm going to put here 5. 1 will go out. So what I'm going to do here is I'm going to put an X here to say that 1 has been taken out of the queue, and that we will no longer start looking at the first in, first out on this line, but rather in the next succeeding line starting at 2. All right, so data page 5 would replace 1 because 1 is the first in of all the 4 data pages on the current page frame. We're gonna copy 2, 3, and 4. The next data page to be called is 1. As you can see, 1 is not there. All right, and it's going to result into a page fault. Now we've got to find out, okay, which of these 4 data pages we need to replace. So again, we'll start at 2 because we've just X'd out 1. So between 2, 3, 4, and 5, which one was first in? So it was, obviously it's 2. So 1 would replace 2 right there. We're going to put an X mark just on top of 2 here. Okay, and then we're going to copy the other data pages in the memory, 5, 3, and 4. Now the next data page is 2. As you can see, there is no 2 in the current page frame, so that would result into a page fault again. And between from among 5, 1, 3, 4, we're going to start looking at 3, and then 4, and then 1, and then 5. Obviously, it's a 3, so 2 will replace 3, like so. And we're going to put an X mark right on top here. And we're going to say 5, 1, and 4. The last one to be called is job number 3. Job number 3 is not in the current RAM, in the current page frames of the RAM. So that would result in a page fault. Again, we're going to look at 5, 1, 2, 4. So you got 4, 1, 2, 5 right there. So obviously 4 would be replaced by 3. So we're going to put here 3. We're going to X out 4. And we're going to copy 5, 1, 2. In the exam, you might be asked, what is the percentage in terms of page fault or page interrupt? As you can see here, out of the 10 page frames, out of the 10 jobs that were loaded into 4 page frames, there were actually 8 out of 10 instances. So that's like 80%, right, page fault. And the page hit is 2 out of 10 in this example, so that's 20% page hit. I hope this has been informative for you, and I would like. So in our second simulation example, this time we're going to use the least recently used replacement algorithm, intentionally using the same set of data pages, all 10 of them, as you can see here, from 1, 2, 3, 4, 1, 2, 5, 1, 2, 3. It's the same set of data page we have for the first algorithm, which is the first in, first out. We're also having, as an example, 4 page frames sizes for the memory. And as usual, we're going to track the loading of all these data pages to the page frames, and from there we are tracking the percentage of page faults or page interrupt as well as the page hit. It is the hope that we're going to find out which from among the 2 algorithms will provide a better page hit given the same set of variables. The least recently used policy, the idea behind this is that the page that is least recently accessed is the best page to remove. So let's see. First item on the agenda, we have data page 1 needs to be loaded to the page frame. 1 is not existing there, so we have a page fault. So we're going to put an F there and 1 right there. And then the next data page will be 2. There's a page fault because 2 is not in the current page frame. So I'm going to put here an F. So 1 will be copied as well. And then 2 would load itself. And then the third one is 3. 3 is not currently in the RAM, so that'll be a page fault. And I'm going to copy 1, 2, and 3. Same thing with 4. That would result into a page fault. And I'll just copy the existing ones, 1, 2, 3, and load 4. The next one is 1. All right, 1 is already in there, so that will be a page hit. So we're going to have an H here. 1, 2, 3, 4. As well as 2, which is the next page to be requested. 2 is already in the current page frame, so that will also provide a hit. So we're just going to copy the rest of the contents of the pages. The next one to be loaded or requested is data page 5. As you can see, page 5 is not here in the page frame, so that would result into a page fault. And the way we now figure out which one to replace from among the lineup here is to look from right to left this time. As you can see, my arrow changes. A while ago in first in, first out, this was pointing from left to right. This time we're going to point from right to left. So we're looking at number 5 here. So starting at its next adjacent number to the left, we got 2. So the algorithm's nomenclature is least recently used. So we're going to find out what is the last recently or least recently used algorithm. So currently we have 1, 2, 3, 4. We're looking for this data pages. So from here, since we're loading 5, we're going to start from here and then work our way going to the left. So 2 is not the lead, well, it's the most recently used, and then 1, and then 4, and then 3. So from among the 4, 3 is the least recently used. So 5 will replace 3 in this case, and the rest will continue to be 1, 2, and 4. And then 1 here would be requested. As you can see, 1 is already in the current page frame, so that will result into a hit. So we have 1, 2, 5, and 4, as well as the next data page, which is 2. 2 is already there, so that would result into a hit as well. So we have 1, 2, 5, and 4. The last one being 3, again, that would result in the page fault. And from here, what we're going to do is, since we're looking at 3 here, the next number to the left, which is 2, we're going to look for the least recently used. So we're looking for the numbers 1, 2, 5, and 4. So here's number 2, here's number 1, here's number 5, and here's number 4 all the way to the left right here. So obviously, hands down, 4 would be replaced by 3. So 3 goes here, 1 loads, 1 is copied as well as 2, and 5. All right, so here what we have is probably that 60% page hit. Oh, sorry, page fault, and 40% page hit. Given the same set of variables and assumptions, I think in this example we have shown that least recently used will execute faster using this algorithm. I hope this has been informative for you, and I would like to thank. Look at several examples of demand paging memory allocation schemes. Demand paging has 2 advantages. It was the first scheme in which a job was no longer constrained by the size of the physical memory. The second advantage was that it utilized memory more efficiently than the previous schemes because the sections of a job that were used seldom or not at all weren't loaded into memory unless they were specifically requested. Its disadvantage was that there's an increasing overhead caused by the tables and the page interrupts. The concept of segmentation is based on the common practice by programmers of structuring their programs into modules, or what we term as local or logical groupings of code. With segmented memory allocation, each job is divided into several segments of different sizes. one for each module that contains pieces that perform related functions. A subroutine is an example of one such logical group. Segmented memory allocation was designed to reduce this page faults. The segmented demand page memory allocation scheme evolved from the two we've just discussed. It is a combination of segmentation and demand paging, and it offers the logical benefits of segmentation as well as the physical benefits of paging. The algorithms used by the demand paging and segmented memory management schemes are applied here with only minor modifications. This allocation scheme doesn't keep each segment as a single contiguous unit, but subdivides it into pages of equal size that are smaller than most segments and more easily manipulated than whole segments. Therefore, many of the problems of segmentation, such as compaction, fragmentation, and secondary storage handling, are moot. One of the biggest, most profound advantages of segmented demand page memory allocation is that it creates a large virtual memory and that segments are loaded on demand. However, the disadvantage to this is that the table handling is quite slow, thereby creating a lot of overheads. We will revisit this technique more in later chapters. For now, for me, this is the best out of the 4 allocation techniques that we have discussed so far. Virtual memory became possible with the capability of moving pages at will between main memory and secondary storage, and it effectively removed restrictions on maximum program size. With virtual memory, even though only a portion of each program is stored in memory at any given moment, by swapping pages into and out of memory, it gives users the appearance that their programs are completely loaded into main memory during their entire processing time, a feat that would require an incredibly large amount of main memory. Virtual memory management has several advantages. A job size is no longer restricted to the size of the main memory, or worse, to the free space available within that main memory. Memory is also used more efficiently because only the sections of a job stored in memory are those needed immediately, while those not needed remain in secondary storage. It allows an unlimited amount of multi-programming, multi-processing, even multi-threading, which can apply to many jobs, as in dynamic and static partitioning, or to many users. It also allows the sharing of code and data. It facilitates dynamic linking of program segments, otherwise known as dynamic linking and embedding. The advantages for me far outweighs the disadvantages provided here in this bullet slide. Cache memory is based on the concept of using a small, fast, and expensive memory to supplement the workings of main memory. Because the cache is usually small in capacity compared to main memory, it can use more expensive memory chips. These are 5 to 10 times faster than main memory and match the speed of the CPU. Therefore, if data or instructions that are frequently used are stored in the cache memory access time can be cut down significantly, and the CPU can execute those instructions faster, thus raising the overall performance of the computer system. A typical microprocessor has 2 or more levels of cache, such as level 1, 2, and sometimes there's a level 3. The difference from among these 3 is very simple. In level 1, which is normally around 2 kilobytes to 64 kilobytes in size, instructions are first searched in this cache. Level 1 cache is very small in comparison to others, thus making it faster than the rest. So this is a smaller size cache, but generally the fastest from among the 3 levels. Level 2 cache is around 256 kilobytes to 512 kilobytes. If the instructions are not present in the level 1 cache, then it looks in the level 2 cache, which is slightly larger pool of cache, but it is accompanied by some latency delay compared to level 1 cache. So level 2 cache is slower than level 1, but it's generally bigger than level 1 cache size. Level 3 is around 1 megabyte to practically 8 megabytes of size. With each cache miss, it proceeds to the next level cache. This is the largest among all the cache, even though it is the slowest. It's still faster, of course, than the RAM. So finally, as your assignment takeaway for this chapter 3, complex memory management system, I would require you to answer this two kind of a research work for you to submit through MS Word document. Probably I would say for each number, probably 1 or 2 pages will suffice. So that will bring it to around 3 to 4 pages in total. I just want you to be very brief and straight to the point. If you can put some figures, tables, diagrams, or screenshots, that will be even better. For the first number, you would be required to use your virtual machine in order to change your virtual memory size. So I would suggest that you do uh, find out how to change the virtual memory for Windows 10, for Windows Server 2012, for Kali Linux, and as well as the Fedora Linux. Again, do not do these changing of the virtual memory configuration on your host machine. For number two, again, this is more of a theoretical research. I would require you to actually research about the multi-core implementation of cache memory. I would really require that you put some footnotes, endnotes, citations using a full APA guideline in providing citation. Anyways, if you have any questions, excuse me, if you have any questions whatsoever, don't hesitate to give me a shout, send me an email, and I will try to respond to your email or request as soon as possible. The deadline for this, I believe, that I put on the Blackboard is the on Saturday at 11:59 p.m. So good luck, and I'll see you next week. Thank you so much.